I will be presenting my final exam for Data 605. Problem 1. Use an R, generate a random variable x that has 10,000 random uniform numbers from 1 to n, where n can be any number you're choosing greater than or equal to 6. Then generate a random variable y that has 10,000 random normal numbers with a mean of mu equal to sigma equal to n plus 1 over 2. I set seed 1, 2, 3 to store our random numbers. Then I set n equal to 10, sigma is equal to n plus 1 over 2, and mu is equal to sigma. I generate the random variable x using the runif function to generate uniform numbers with 10,000 observations from 1 to n. I then create the random variable y using the rnorm function with 10,000 observations. Mean is equal to mu, standard deviation is equal to sigma, and now I create a data frame of our random variables. You can see here the summary of x and the summary of y. Next, the probability. Calculate as a minimum the below probabilities A through C. Assume the small letter x is estimated as the median of the x variable, and the small letter y is estimated as the first quartile of the y variable. Interpret the median of all probabilities. I create the our variable small x, which is equal to the median of the random variable x, and small y is equal to the first quartile of y. Question A. Probability that x is greater than the median of x, given that x is greater than the first quartile of y. That is the likelihood of event A, given that B is true. In order to do that, I calculate the probability of AB by filtering the rows where the random variable x is greater than the median of x, and the random variable x is greater than the first quartile of y. And I count the rows. Next, I get the probability of x being greater than the first quartile of y, and I count the rows, and from there I'm able to divide probability of AB divided by probability of B, and I round that answer to 2 decimal places, and I get 0.55. Question B. Probability of x being greater than the median of x and y is greater than the first quartile of y. This is the probability of the intersection of A and B. To get the answer, I filter the random variable x being greater than the median of x, and y is greater than the first quartile of y. And I divide the number of rows by 10,000, which is our observation, and I round that number to 2 decimal places, which is 0.38. Question B. Probability that x is less than the median of x, given that x is greater than the first quartile of y. That is the likelihood of the event A, given that B is true. In order to do that, I filter out the rows where x is less than the median of x and x is greater than the first quartile of y, and I count the rows. Next, I get the probability of B, which is the rows where x is greater than the first quartile of y, and I count rows, and after I can divide the probability of AB divided by B, and I round that answer to 2 decimal places, and I get 0.45. Next, investigate whether the probability of x is greater than the median of x and y is greater than the first quartile of y is equal to the probability of x greater than the median of x times the probability of y being greater than the first quartile of y by building a table and evaluate the marginal and joint probabilities. I calculate the probability of each, and then I stored that into a matrix, and you can see here a matrix with the marginal probabilities on the outside and the joint probabilities on the inside. I'm asked to find the probability of x greater than the median of x and y greater than the first quartile of y, which is 0.375. And I then multiply the probability of A times the probability of B, which is equal to 0.375, which is very similar to what we see here. And I assume that this is a rounding error, so I would say that they are independent of each other. Check to see if the independence holds by using the Fisher's exact test and chi-square test. What is the difference between the two? Which is most appropriate? Both the Fisher's exact test and the chi-square test are both used to determine if there is a significant relationship between variables. Chi-square test is used when the sample is large, and the Fisher's exact test is used when the sample is small. Here, the chi-square test is appropriate since there is 10,000 observations. I first generate the table of our observations, and here you can see the table. I run this table through the chi-square test function, and I get a p-value of 0.7995. With this p-value, we cannot reject the null hypothesis. Then I use the Fisher's test function. I run my table through the Fisher's test function, and I get the same p-value. And with these two tests, we cannot reject the null hypothesis. The independence remains true. Problem 2. You are to register Kaggle.com free and complete in the House Prices Advanced Regression Techniques competition. So first thing first, I load the dataset, and then I remove the outliers by using the boxplot stats function, identifying the outliers, then finding the rows, and then filtering out the rows. Descriptive and inferential statistics. Provide univariate descriptive statistics and appropriate plots for the training data set. Provide a scatter plot matrix for at least two of the independent variables and the dependent variable. Derive a correlation matrix for any three quantitative variables in the data set. Testing the hypothesis that the correlation between each pairwise set of variables is 0, and provide an 80% confidence interval. Discuss the meaning of your analysis. Would you be worried about family-wise error? Why or why not? First thing I do is get the descriptive statistics of the data set house prices train. You can see the summary for the categorical and the numerical variables here. Next, I get the distribution of the dependent variable sale price. After removing the outliers for sale price, this is the distribution of sale price. So next, scatter plots. I get the independent variable overall quality and our dependent variable sale price, and I perform a scatter plot graph. Here you can see it's positively correlated. Next, I create a scatter plot of the above ground living area, which is our independent variable, and our dependent variable sale price. Again, it's positively correlated, and you see outliers of the above ground living area. Next, I find the correlation by creating a correlation matrix of the same variables that I showed, with sale price, overall quality, and above ground living area, and I store as a matrix. Next, I test the hypothesis. In order to do so, I use the core test function with our independent variable and our dependent variable using a confidence level of 0.8. Here, the p-value is very low, so we can, and we see here the sample estimate of is 7.78, which means that the overall quality and the sale price have a correlation of 0.78, and we're saying here that the p-value is very small, and we reject the null hypothesis, and we're saying that they are related. Is the alternative hypothesis is true, correlation is not equal to 0. And for our population, we have 80% confidence interval between 0.77 and 0.79. Next, we use our second independent variable, above ground living area, to our dependent variable sale price using confidence level 0.8. Again, we see a very low p-value. True correlation is not equal to 0. We get a sample estimate of our correlation, which is 0.66, and with the 80% confidence interval, 0.64 to 0.68 is our population correlation. Next is the family-wise error rate, which is this formula right here. So the independent variables have strong correlations with our dependent variable. Here we're not worried about family-wise error, as the number of tests are low and the p-value from our tests are very low. Thus, we can reject the null hypothesis. Next, linear algebra and correlation. Invert your correlation matrix from above. This is known as the precision matrix and contains variance, inflation factors on the diagonal. Multiply the correlation by the precision matrix, and then multiply the precision matrix by the correlation matrix. Conduct LU decomposition on the matrix. So in order to calculate the precision matrix, I use the solve function on our matrix, the correlation matrix that we created. And this is the precision matrix. Next, I multiply the correlation matrix with the precision matrix, and I round the answer to 2 decimal places, and we get the identity matrix. We do the same thing, but first we have the precision matrix multiplied by the correlation matrix, and we again get the identity matrix. Next, I use the LU function from our MATLib library, and we get the lower triangle with 1 across the diagonal and values on the lower triangle, and the U matrix where we have values on the upper triangle. Next, the calculus-based probability and statistics. Many times it makes sense to fit a closed form distribution to the data. Select a variable in the Kaggle.com training data set that is skewed to the right. Shift it so that the minimum value is absolutely above 0 if necessary. Then load the mass package and fit this TR to fit an exponential probability density function. Find the optimal value of lambda for this distribution, and then take 1,000 samples from the exponential distribution using the value REXP 1000 lambda. Plot a histogram and compare it with a histogram of your original variable. Using the exponential PDF, find the 5th and 95th percentiles using the cumulative distribution function CDF. Also generate 95% confidence interval from the empirical data, assuming normality. Finally, provide the empirical 5th percentile and 95th percentile of the data and discuss. First thing to do is find a variable that's skewed right, and here is the distribution of lot area, and so I will be using the variable lot area. So I fit the lot area variable to an exponential probability density function using the fit this TR function. We find the optimal lambda, which is this value here, and again we get that same value here. Next, we run 1,000 samples using the REXP function, generate 1,000 samples using lambda, and I store that in a data frame called optlam. Next, I graph the histogram of the variable. Here we see that the range is much smaller than what we saw above. This goes to 150,000, while this goes to 80,000, and is much smoother. Next, 5th and 95th percentiles using CDF. So I use the QEXP function with our percentile 0.05 and the rate lambda, and then I get the 95th percentile using the same function but replacing it with 0.95, and this is our 95th percentile. So next is the 95% confidence interval. I calculate the marginal error, getting the sigma of lot area, the observations, the z-score, put that in a formula, then I get the upper bound by getting the mean of lot area plus the marginal error, and then the lower bound by subtracting the marginal error. And then we can say we have a 95% confidence that the interval, the population's mean is between 9,789 and 10,521. And then lastly, I get the percentiles of lot area of the empirical data. The 5%, the 5th percentile is going to be 3,196, and the 95th percentile will be 16,783. Next, modeling. Build some type of multiple regression model and submit your model to the competition board. Provide your complete model summary and results with analysis. Report your Kaggle.com username and score. So after going through multiple iterations of the LM function, this is the variables I ended up with. And here we see the summary. We see adjusted R-squared score of 0.77, which is the highest I was able to achieve. And next we look at the residuals. So here we see there is variation towards the extremes. The histogram is normally distributed, except for these outliers over here. And the QQ plot shows, again, there are outliers at the extremes. Using the above linear regression, my Kaggle score is 0.75094. Username Diego Correa 614, and this is my submission and score. Thank you.